It's 11:10, so why don't we get going? Welcome and happy Friday. So we mentioned before, I guess, when we were doing the wave, that the particles aren't the thing that moves along. And another way I have of sort of visualizing this in my head as I think about waves and a field of grass that you can sometimes see moving along. Obviously, the grass isn't the thing that's moving along because it's all rooted, right? So what's moving is the energy, I guess, and also the pattern kind of moves along. And so that's going to be a recurring theme here, is that even as particles are moving up and down, the pattern can move from left to right. And we've got Alvina with the wireless mic. Do you have anything yet? No? Hey, feel free to interrupt me anytime. Just click it on and shout out. And also anybody, if you just, something comes up and you want to yell out, that also works for me, as long as I can hear you. So good. The course evaluations are coming along. We got until December 9th to do this, so there's still some time left. But so far, we're up to 0 point, almost half a point for everyone's mark. And so, obviously, I have to submit an integer at the end of the semester onto Acorn, but it's your actual mark is going to be a decimal, and then I'll just add this, then I'll round it. So this could boost you up, possibly. So if you haven't done it yet, you can click on the Course Evaluations tab on your Quarkus and do that. Okay. What we didn't do last time is this equation, which isn't derived anywhere in your book. The derivation sometimes comes in first-year textbooks, sometimes it doesn't, and you're going to have to use something like the curvature, something. It's not an easy one to do. We're not doing it. So we're just going to state it, which is that the speed of transverse waves on a string stretched with some tension, and this looks like a little spring actually, is v equals the square root of f over mu. So what is that? Mu is not the coefficient of friction. We're starting to run out of letters here, even Greek letters. So we're reusing them. It's the letter recycling program. This is, again, mu. And it's mass per unit length in kilograms per meter. And also, by the way, F is the tension. And I'll just note here, we use F for tension in newtons, I guess. Because if we used capital T, it might get us confused with the period of the wave. So once again, we're running short of letters here, because in chapters 10 and 11, we use T for period in seconds. So to avoid confusion or create new confusion or whatever, we're going to use F. And it's a force, right? So that's good. But the more you stretch the string, the more force you pull on it, the faster the waves travel on it. And also, the thicker the string is, so the more mass per unit length, the slower waves go on it. And another good way of kind of remembering this, if you play a stringed instrument, then the pitch of the string is going to be related to the speed that waves are bouncing back and forth, because you're creating standing waves there. So if you have a guitar and you pluck the string and you increase the tension, F, by cranking up the knob, you're going to increase the speed of waves, you're going to increase the frequency. Or if you have thicker strings and they're all at the same tension, which they tend to be, you tend to try to get all 6 strings in your guitar to be around the same tension so it doesn't torque your guitar around. In that case, the thicker strings will have slower speed and they'll have a lower note. And so you often see, the low E has a thicker metal string, and the high E has a tiny little thin string. So there's always your high E string that breaks first. Okay, so we can do a little I also want to do an example question. An 80-kilogram climber hangs from a rope 20 meters below a rocky overhang. The rope has a linear density of 37 grams per meter. So I'm going to write that down as mu is equal to 0.037 kilograms per meter. So in order to use this equation, you're going to have to convert things to SI units. It's always a good thing to do. And a gram, strangely enough, is not an SI unit. You would think it is, but in fact the SI unit for mass is kilogram, so you have to divide by 1,000. And somehow there's a rocky overhang or something, if you can imagine, and the rope hangs over like this, and there's a climber dangling from the rope somehow. And it's a 20-meter distance. And the question is, what's the time? How long would it take a transverse pulse to travel the length of the rope from the climber to the overhang? And it also gives you that the mass of the climber is equal to 80 kilograms. So what I'm going to do is, if you do the force diagram of the climber, it's just that there's a tension going up, F, and then there's mg pulling down, and the climber's in equilibrium. So if the system here is the climber, climber does not accelerate. Accelerate. So if you put plus y is up or something like that, then F minus mg is equal to 0. So F equals mg. And then the speed of waves is the square root of mf over mu. And also, v is equal to d over t if it's a constant speed. So we're going to assume constant speed, constant wave speed. And so we just kind of plug things in here. So t is equal to d over v, or d times the square root of mu over f, something like that. So 20 meters times the square root of 0.037 divided by 80 times 9.8. So maybe I should see d, if we want to list all the things we know, mg. Okay, and so I plug those into my calculator and I got 0.14 seconds. But what's interesting is note, I'll just note here, that we neglected the mass of the string, or the rope. And the reason I did that is because we neglected the mass of the rope when calculating tension. And I guess I was thinking of the tension at the bottom where the climber is hanging, but in fact, if you think about it, the tension at the top of the rope also has to hold the entire rope plus the climber. So I just wanted to check that the mass of the rope is equal to 20 meters times 0.037 kilograms per meter. We can calculate that out, and I got 0.7 kilograms. So this is, I guess, a lot less than 80 kilograms. So I guess it's okay. It's sort of less than 1%, I guess. It's okay to neglect mass of rope. I think really what we've done here, what would happen is that the tension would be higher at the top of the rope because it's suspending not just 80 kilograms, but 80.7 kilograms. And then the tension would be less at the bottom of the rope. So the wave wouldn't travel at a constant speed, and then the problem would be way harder to do. But again, when things are less than about 1%, I just say, well, two significant figures, it should be okay. Sort of like the small angle approximation. How are things going on the discussion board? Yeah, things okay? Anybody else? Good. Should we do a little learning catalytics? For a wave pulse on a string to travel twice as fast, how should you adjust the tension, F? And shall I write the equation up again from before? It is V is equal to square root F divided by mu. Check your neighbor. I think I'm just going to dial in 30 seconds on this thing for discussion. This is a pretty straightforward one. You check your neighbor. That's my timer. Should we click in something here? I have 224 responses. Maybe 5 seconds? Going once, going twice. Factor of 4 is the most popular answer. Also the one that I like. So yeah, it's just something like, since it's a square root, remember that here F is equal to the tension, which is kind of strange, but that's okay. It's a force. So if force goes up by a factor of 4, then I guess the speed will go up by a factor of the square root of 4. So like A. Okay. So the subject that we're getting onto next is sinusoidal waves. So, and then what's our plan here? We're going to do sinusoidal waves for a while. Then we're going to talk a little bit about wave reflections, and then we're going on to intensity in the decibel system. So 3 more things to do. So, sinusoidal waves. This is a little very slow stop animation of a traveling sinusoidal wave. And what I want you to note here is that the shape of the pattern doesn't actually change. It just shifts along from left to right. And at the same time, the particles are just going up and down. And in fact, the particles are just moving in simple harmonic motion. So this is chapter 11, so we're talking about a real wave that moves along, but there's a chapter 10 concept, which is that any individual particle is oscillating with simple harmonic motion, and so are its neighbors, but just a little delayed or advanced. So there's 4 numbers that go along here. There's wavelength, which is like the distance between crests along the direction of wave travel. There's period, which is, it's, again, since each particle is moving with simple harmonic motion, it's actually the period of that. Okay, so for any point in the wave, or any position x, it's going to go through a complete cycle every period. And 1 over the period's the frequency. Good. And then amplitude. So it's kind of funny. These last 3 are kind of repeated from chapter 10, aren't they? And our new concept here is really just wavelength. But there's another one. There's a 5th number, which is new for this chapter, which is wave speed. And wave speed is the wavelength divided by the period. Because if you think of that wave traveling along, a crest is going to move a distance of 1 wavelength in the same amount of time that it takes a particle to go all the way down and back up again. Start at a crest and go down and up. If that makes sense to you. So that's why you can take sort of like a distance per time is wavelength divided by period. So let's see if you guys can do this. I'll give you a minute to do this one instead of, this one's a little harder. Okay, and there'll be 2 questions on this. The first one, and they're both about this. A traveling wave moves with a certain speed, wavelength, and period. It was created by an object which is oscillating with simple harmonic motion. So at one end, we're just doing simple harmonic motion and the waves are traveling along. If the period of the oscillator decreases, what should happen to the speed of the wave? Now, put 1 minute for discussion with your neighbor. What do you think? Oops. How are we doing here?
Professor,
Yes,
we have
yes.
a question on the discussion board. So it says, is wavelength the same as period? Or is there a situation where they will have different values?
Yeah, I think I understand the question. So this is the weird thing, is that people are looking at a couple of different equations. There's two equations that are flying around here, which is this and this. So it's kind of like which to use, right? Should we just let's do stop, and we'll do. This isn't really going the way I was hoped here. Yeah, well, let's. That wasn't maybe so great. Let's go back to. Let's go to this. Maybe this is better. Hold on. I think I just showed you. Maybe not what I wanted to do there. Okay, let's go back to this question. Different. What happens to the wavelength of the wave if the period decreases? So, so what I'm trying to say here, I guess, is that, and this is the key message for everyone to walk away with, is that the speed of a wave in a medium depends on the properties of the medium, not the wave. For example, if I have a high-pitched voice or a low-pitched voice, it doesn't change the speed of sound. Okay, speed of sound is the speed of sound. All right, it's 340 meters per second. That's determined by the density of the air and the temperature of the air, and obviously the mass of the air molecules. Okay, as my voice travels out. If I have a different period of oscillation of my voice from low or high, it doesn't change the speed of sound. The speed of sound is the speed of sound. And with this wave traveling along, the speed of a wave is determined by the tension in the rope and the mass density of the rope. That's what's determining the speed, not the period that you're oscillating one end of it. Follow me? So don't just blindly plug into an equation, because the wavelength wasn't constant. Okay? Change the period, you're going to change the wavelength, not the speed. So sorry about the trick question. Why don't we do the other one again? You guys get this one? We'll do a redo. So what do you think about this? Actually, let's do this question first. The speed is the same, And don't forget, so you're still using this equation now, which is that the speed does equal lambda over t. But what I'm saying is, of these three letters, the one that's a constant is v, not lambda. So 10 seconds. Or so. Okay. Going once, going twice. Okay. Yeah, it's just lambda equals v times t, right? You decrease the. Another way of looking at this is lambda equals v times the period. V is constant because it's determined by the properties of the medium, not the wave. And just going back to this one real quickly, we definitely need a round 2. Use this. Okay, so lambda is not a constant when you change the period. Change the period, change the wavelength. Okay. Okay. Yeah, this is going a little better. This is okay. Leave that up for a second. All right. So sometimes it's good to just go through these things. What's next? Oh yeah, this thingy. So I sent you an announcement today with a do-it-yourself demonstration. So this is going to end up being worth 0.2 of one Learning Catalyst question on Monday. There is no submission for this or anything, so don't worry too much about it. It looks like, but I think it's definitely worth doing because you'll learn about waves from this. Is this animation, which you have to click on. You might have to kind of install something, but it looks like this. But I think what I was actually showing is that if we take a position versus time graph and you go up slowly, let's go slow motion, lower the tension. Let's slow this down a little bit. If I go up slowly and then down quickly, then it sends a wave. Let's get rid of the damping too. It sends a wave shape along that's kind of reversed. You see how the trailing end on the left is the last thing I do, and the first thing I do for low t, I go up slowly, and then for high t, at t equals 3 or something, I go down quickly. That's why when you compare a history graph to a snapshot graph, the snapshot's what you see, and the history is just making a plot of the wrench versus time. Right? So anyway, so you can play around with this yourself. I've got some stuff about damping and fixing. There's 7 questions. Should take maybe 20 minutes or something to go through. But this question I'm going to ask in class, which is, can you find a frequency for which all the green beads are nodes? So we're going to do some standing wave stuff. What happened here? Off it goes out the window. Okay.
Professor?
Yes.
We have 2 more questions.
Yeah, please.
So the first one is it okay to put that if the property of the target medium stays consistent, then the speed of the wave within that medium will be constant?
Yeah, the properties of the medium stay constant, then the speed of the waves is the same. Yeah, exactly.
And the second one is, for the formula of the speed of the wave, is the force always tension? Can it be anything else? And can you explain why we use F instead of T as a symbol for force in this equation again?
Yeah, both great questions. So yeah, it's the F equal, or V equals square root of F over mu. So first question is that, well, that's the speed for transverse waves on a string. So for example, I pull this rubber hose out some particular tension, it's going to have a speed of waves. And if I increase the tension by pulling more, then wave speed is going to go up. Or if I have a thicker hose, then the wave speed is going to go down. So, but there's other kinds of waves. For example, sound waves. So there's going to be a different equation for that. Or whatever kind of waves we have. You know, that torsion wave or something. There's different waves, different kinds of waves will have a different equation. So that's a specific example of a transverse wave on a stretched string. And yeah, the reason we use F instead of T was because I don't want you to get confused with period, which is using capital T in this chapter. And like I say, I'm kind of running out of letters. These are all good questions. So while we're at it, this rubber hose that I'm holding is attached. Tyus has tied it in a knot to the railing at the other end. And so that's what's called a hard boundary. And you're going to be investigating this when you do that learning catalytics homework. I think there's fixed end, loose end, and no end, where they just open a window and it's tied to something very far away. So when a wave pulse, which is positive, hits a fixed end, which cannot move, then what will happen is that energy from the pulse will get kind of absorbed in whatever the knot there or the hook. That momentum will get stored for a minute, and it'll reflect the wave pulse to be negative on the way back. I don't know if we can try to see it in this actual hose. I don't know if my video guy can zoom out or something like that to see this entire stage here. Can you do a zoom? Thank you. Or an unzoom or whatever, wide angle. I'm going to hit this up, maybe an upward pulse. Do you see the downward pulse that reflects off the right end? And there's a bunch of pulses. Let's do it one more time. So up, and you get a reflected pulse, which is down. The other thing I can do, I guess I can send a negative pulse and see what reflects off that end by hitting it down. See the positive pulse that comes? So it flips the pulse when it hits the right end. So moral of the story is, with a single pulse like this, it's easy to see a reflection. So boom, it goes back and forth. For a sinusoidal wave, the reflections begin to overlap the original wave. So if I just move this end up and down, like a simple harmonic oscillator, then that's what happens. So this is kind of weird. This is not at all what you might expect. You're not seeing a sine wave going out the window because the other end's fixed. So instead you see this, and this is what's called a standing wave. So, you know, it's almost like you're doing skipping or something like that, right? It goes around and around. You get a just what you would expect. It goes up and down. But what's interesting, you can change the frequency. Let's see if I can do this. I don't know if you've ever done this with skipping. So that it kind of flips up and down on either side with a point in between that doesn't go up and down. It's called a node. You see where it's sort of just flipped in the middle? It doesn't move much. And then if I change the frequency even more, let's see if I can do this higher, I can get two of those intermediate points called nodes. And then in between the nodes, there's these high oscillation places where it's called an antinode, actually, where it's most of the oscillation. So that's what's called a 1, 2, 3, third harmonic. So we're going to talk all about standing waves when we come back after the weekend. But that's your basic idea. And then the other thing you'll see on your simulation for your homework is reflection from a soft boundary. So imagine that instead of a hook, what we have is a vertical pole, which holds the tension, but which provides no vertical force at the end. Then what will happen is when this string hits the end, it just slides the ring way up, even higher than the amplitude of the pulse, twice as much actually. And then when it comes back down again, you have a positive pulse that's reflecting. So it does not invert the pulse when you have a loose end. And you'll be able to see that, I think, when you do your simulation. It's a little harder to set up in a real thing. And that's 2 out of the 3 things I was going to do today. Third thing, last 20 minutes of today's class, I'm going to go through wave intensity and the decibel system. So we're going to talk about sound a little bit, I guess, more. Okay? Thank you for some great questions on the discussion board as well. Okay, last thing for today. We'll spend 20 minutes talking about wave intensity. And this is going back to a concept of energy and power, actually, which is that if you buy a speaker and you want to know how powerful it is, it's about how many watts of power it puts out into sound waves. Okay, so a speaker has some power, and then the wave fronts. Again, if you think of this wave as traveling out in every different direction, you can imagine that energy per second is spreading out over larger and larger surface area of these hemispherical wave fronts, I guess. So this is the concept of wave intensity, is the power divided by the area. Let's see what we've got here. If the wave spreads out uniformly in all directions and no energy is absorbed somehow, so you can also have loss of energy that's due to, I don't know, heating the air or something like that. We're neglecting that. Even still, if you get farther away, it gets quieter. And the reason is that the intensity, I, is going to be equal to the power divided by the area, 4 pi r squared. Which is, so P is equal to the power in the entire wave, and 4 pi r squared is this surface area of a sphere. A sphere. And what these are is concentric spherical wave fronts, all centered on the source of the sound. At a greater distance, R2 greater than R1, what happens is the intensity is less, not because the power has gone down, you haven't lost any energy, you're just spreading it out over more surface area. So keeping with this example of listening to sound, I guess what I'm saying is that if you're farther away from a sound source, it sounds quieter. And the reason is, I guess, that if you think of your ear, it has a little hole which is receiving the sound, and that has like a collection area. I kind of like to think of it as maybe if you have a bucket that's collecting rain. The rain is coming down. If you have a larger area bucket, you'll collect more rain per some unit of time or something like that, right? So if you had a larger ear with more area, you would collect more of that intensity. Or conversely, if the intensity drops, the amount of sound that you're going to hear is going to be just the area of your ear multiplied times the intensity to give if you see what I'm saying. And so it's the intensity that reaches our head that determines how loud the sound will sound. So it's not just the power of the source, but it's also your distance from the source that matters because of this just geometric effect of spreading. That is why further sound sources seem quieter to us. It's also why things seem less bright. If you have a candle on the other side of the lake, that energy in the light wave actually that's traveled out gets spread over a bigger sphere. Okay? So there's a 1/r squared law for intensity of a lot of different sources like this.
Professor,
yes,
we have a couple more questions here.
Great.
So the first one is, why is wave pulse at the end higher than waves from the initial disturbance?
I don't know. You mean that? I don't know why it would be any higher. Seems like the wave pulse should be the same height as it goes along, or maybe a little less if you're starting to lose energy somehow.
The second one is, could you explain exactly what constitutes a soft boundary?
Oh, yeah. So a soft boundary, so it's sort of weird. it's a change in the medium because there's the rope ends, I guess. So, and a hard boundary is where the rope ends and there's a vertical force which wants to hold it steady. And a soft boundary is the rope ends, there's no more mass, but the end is free to travel up and down, I guess. So, and it does, both of those will create a reflection. Any change in the medium tends to cause a reflected wave. It's a really good question. Third one?
Another question is a new sphere created with every pulse?
Yeah. Every time there's a crest, you get a whole new sphere coming up, and there's spheres for every wavelength. So actually the distance between the concentric spheres is one wavelength, because these are locus of the crests.
And the last question is, for intensity, why do we use the surface area of a sphere, and where would this equation be applicable?
What to Google? I don't know. It's called a point source. So you can have maybe a plane wave going along where the area is not a sphere, it's just whatever the cross-sectional area of a square is or something. Intensity could remain constant. But if you have a point source, then I think that as the waves travel out, and if they travel equally in all directions, so it's an isotropic source or something, then that you're looking at a spherical surface. Spherical waves spread over even larger areas, so the intensity decreases. Something like that, P over A. So P over A is sort of like a general formula for intensity, and for a point source, then you get spherical wavefronts, and you get P equals, or intensity is P over 4 pi r squared. You want to try it? Stop this round 2. I don't know what you think of this one. A speaker hangs on a wire in the middle of a huge auditorium. It is a distance of 9 meters away from your ear. So I think if you do 4 pi times 9 squared, you get 1,000, roughly. So when you crank up the speaker to 20 watts, what's the intensity that reaches your ear? I've made it a big auditorium so that you don't get reflected sound waves all over the place. Just the sound you're hearing just from the speaker. Thanks for these good questions on the discussion board. Give you 1 minute to discuss with your neighbor, if you have a neighbor. And MW is a milliwatt, I think. Okay. You guys have an answer? Going once, going twice. And the survey says, so it's going a lot better. I was looking for 20 thousandths, right? Because you divide by 1,000 meters. So likey. Another way of saying is 20 milliwatts per meter squared. So let's sum up. So let's remember what sound is actually. It's a pressure wave, right? So it's a longitudinal wave, meaning that the air molecules are oscillating parallel to the direction that the sound actually travels. But when that happens, like when we did that longitudinal wave, you got closer and farther from your neighbors as you shifted back and forth. So there's a density or a pressure aspect to it as well. Okay. Sound waves involve small changes in air pressure and density associated with the back and forth motion of the air as the wave passes along. So you can make a plot of pressure versus time, and that's all sound is. And that's in fact what you store in an MP3 when you have a song on your phone. You're just storing pressure versus time. And sometimes two pressure versus time graphs, one for your left ear and one for your right ear. But that's all that sound is. And if you crank up the volume, you just get a higher amplitude of pressure variation. So this is from a song. This is, I don't know what song this is, but it's a little portion of a song. This is the pressure versus time. But if you do a higher volume, you get a higher air pressure. So this would actually be a low intensity, so a low watts per meter squared. So by intensity, watts per meter squared is low. And this is a higher intensity. So this is how you actually carry this energy along the wave, is with pressure variations. Sound wave. Okay, so there's more watts per meter squared in this wave on the right than there is on the left. And then there's the question of the human impact of these sound waves on your eardrum and whether it can cause hearing damage and things. And also there's the really interesting fact that our ears are, I guess, have evolved to be able to detect and process a huge range of intensities. So we have this thing called intensity level, which is a number that's made up to try to describe intensities. I think it's mostly for like bylaws and things, for if you're going to try to say what's a safe level of sound intensity. People don't like using watts per meter squared because the numbers are too big, so we invented a decibel system to make the numbers a bit more manageable. The decibel scale, it'll look a little odd to you. It's got a logarithm in it, but it's due to the fact that the human ear is sensitive. Not only sensitive, but it also is able to hear very high intensity sounds without getting damaged. In terms of intensity, the sound of a jet engine, for example, is a billion or something like 100,000, million, billion, trillion times more powerful than the smallest audible sound. So the threshold of pain is 10 to the 12 times the threshold of hearing. That's a big difference. So you have this thing called beta, is 10 log I over I0, where beta is a number called intensity level. It's in decibels, is the unit. And I0 is 10 to the minus 12 watts per meter squared. This is just a reference called the threshold of hearing. So if you do the logarithm of 1 on your calculator, does anyone know what log 1 is? It's 0. Nice, okay. Some people know logs, okay. So what is logarithm? Log base 10, it's the number that you raise 10 to get the number. So logarithm 1, what do you have to raise 10 to the power of to get 1? You raise it to the power 0, because anything to the power of 0 gives you 1. So, and if you have a sound that's 10 times more powerful, 10 over 1 is going to be 10. So logarithm of 10, what's logarithm of 10? Anybody? It's 1. Very good. So, and then 1 times 10, because there's a 10 out front, it gives you 10. So you get 10 decibels. But a sound that's 100 times more powerful, logarithm of 100 is, does anyone know? 2, right? The number you raise 10 to get 100 is 2. So 2 times 10 is 20. So 100 times more energy, or watts per meter squared, gives you 20 decibels. So, or 1,000 gives you 30 decibels. So this is a chart from your textbook, your e-text, showing intensity in watts per meter squared for various different things at a certain distance. They don't tell you always the distance. But it goes from the threshold of hearing threshold, which is 10 to the minus 12 watts per meter squared. You can just hear it. All the way up to what's called the threshold of pain, 120 decibels. Above this, then you're probably going to get ear damage pretty quickly. But the point is, for every multiplicative factor of 10 in the actual energy gives you additive plus 10 on this decibel scale. And I think what I want to impress upon you is that the real thing in physics is the intensity. And this intensity level was just invented for humans to try to have a nice system that uses smaller numbers.
Professor,
Yes,
we have
please.
2 more questions.
Great.
The first one is, if in a sphere the sound travels over a bigger area, why do you hear best in a spherical room like Con Hall?
Oh. Well, that's a good question. I mean, this room has reflections, I guess, off of all the surfaces. And so in real life, what happens is that the sound waves travel 340 meters per second and reflect many times off the walls, and you get reverberation, and even a reverberation time in a room like this, which will be different because of the shape of the room. So you're talking about architectural acoustics, which is something I'm interested in, but it's a little beyond, I think, this course. But.
The second
what's the
question is, does the area always have to involve a sphere? Can it be any other shape?
Yeah, so that's a good question. So yeah, the intensity is just power divided by what's called cross-sectional area. So it's the area that's perpendicular to the direction of the wave. So for example, you can use that equation to find the intensity and the power for like the circular opening of your ear or something like that, where you'd use pi r squared for your ear, radius of your eardrum or something. So it can be any surface. Great questions. You want to do 2 more quick questions? We got time. And then we'll be done. 2 quick questions on intensity versus intensity level. First question, and it's the same basic situation, but in the question 5, I'll phrase it in terms of intensity. And for question 6, which we'll do in 2 minutes, it'll be phrased in terms of intensity level. So, and remember, intensity is the easy one. You just use physics, okay? It's energy, right? So 10 times the energy is going to give you 10 times the intensity. One singer produces an intensity of 10 to the minus 4 watts per meter squared if you listen to it at a distance of 3 meters away from the singer. So if you had 10 singers all standing in a group, all singing with that same kind of level of voice, will be the intensity at 3 meters. Feel free to discuss with your neighbor. And pretty soon I'm going to ask about sound intensity level. Good, maybe about 10 seconds to 15 seconds to click in. Okay. Going once, going twice, and yeah, this was the one I liked, was 10 to the minus 3, 10 to the minus 3 watts per meter squared, meaning that you're just multiplying. There's 10 singers, so there'll be 10 times, 10 times the power over the same area. And so I would just say 10 times the intensity. So that's the idea. If you had intensity level, the question would look like this. And this might be more similar to something you might get on the final exam because it's using the decibel system. One singer produces an intensity level of 80 decibels when she sings at a distance of 3 meters from a listener. It's the same question, but rephrased, okay? If you get 10 singers together who sing at the same volume, same distance, what will be the intensity level that you're going to hear now? 81 decibels, 90 decibels, 100 decibels, or 800 decibels?
Professor,
Yes.
I have another question.
Last question,
So,
yes.
thinking about the shape of Cone Hall again and
Yeah.
how it could affect sound, could an ellipse-shaped building or structure focus all the sound into one location?
So an ellipse can focus from one, ellipsoid can focus from one focus. Like if all the sound was at one place, it would focus it to one other place in the room. So that's, I guess, if you have perfectly reflecting surfaces. Yeah, I think apparently the best for opera is to have a rectangular shaped room for some reason. Audiences like that. Okay, I think I'm going to leave it at this. I'm going to show you this answer, which I like 90 decibels. You're up by a factor of 10, so you add 10 to the decibel level. And that is it. Don't forget to look at this little PDF if you want over the weekend and play around with this FET animation. We'll talk more about that on Monday. Hope that doesn't wreck your weekend. Anyway, time between now and 11 on Monday. See you later.